the 30th lecture. In this lecture, we'll study a summary of Markov processes we have been studying for the last few lectures. A Markov chain is the basis. We studied that a Markov chain is the basis of a Markov process. A process is supposed to be taking one of the many states that are represented in a Markov chain. And the transition probabilities from going state I to state j, for example, is represented as small p sub ij, the transition probabilities. According to these transition probabilities, the process takes on any state I during the process goes on for different times. And we also studied that these time intervals are discrete time. They're not continuous. We studied only discrete time processes with finite number of states. The number of states are always limited, countable. They're not uncountable. They are discrete time intervals, and transition probabilities are this Pij is the transition probability, the probability of going from I to j. And we also studied that Pij, if we sum Pij over all possible values of j, it comes out to be 1. This means that the sum of all outgoing arrows from any state I is 1 for all I is 1 to m, where m is the total number of states in the state space of a Markov chain. Right. We also studied that Markov property for first order Markov processes that we study in this course is that if we want to calculate the probability of x at time n plus 1 given n, the state of the process at n, state of the process at n minus 1 up to the state of the process at time 0 is only dependent on one recent value and is independent of all previous values. This is the Markov property for a first order Markov process that we studied in this course. Right, so modeling of a physical real world situation using a Markov chain is an art. Converting a physical problem into a Markov chain and then applying the basic rules. Right, perhaps this is the purpose of this whole stuff that we studied in this segment of the course. So having optimized number of states given a real world problem, it's also a challenge. It's an art and requires a lot of practice. So questions are mainly of two types. You want to calculate probability in finite time or in infinitely large time, or we also call this as SS behavior, steady state behavior. So we studied a lot about steady state behaviors in Markov chains. The steady state behavior is actually the long-term behavior. We have already studied that. And we studied that in a Markov chain, the states are mainly of two types. They are either transient or they are recurrent. If they are transient, this means the process, as the time passes, the process can leave that state and may not return to that state again. In a recurrent states are they compose and they build classes. So in this chain, for example, we can build a recurrent class by using state number 4 and 5. And given this recurrent class, once the process enters into this class, it remains there forever. In this chain, there is another recurrent class that we have here, RC2. And if the process enters into this recurrent class, it remains there forever. So either we have recurrent classes or transient states in a Markov chain. Right. We further studied that these recurrent classes can be aperiodic or periodic. The states in a recurrent class can be periodic or aperiodic. If the recurrent class is periodic, this means the states that are in that recurrent class can be further divided into different subsets. Subset 1, subset 2, subset 3, S1, S2, S3, and all the arrows that come out of S1, subset 1, they enter into subset 2, and all the arrows that come out of S2 subset 2, they enter into S3, and all the arrows that enter that emerge out of SK, K is maybe K is the number of subsets that the states of this recurrent chain are divided in. So all the arrows that emerge out of SK, they enter in the first set S1. So if we see a periodic behavior like this in a recurrent class, the class is a periodic class. Otherwise, the recurrent class is aperiodic. Right, so Rij, the n-step probability after n time steps, Rij starting from I, what is the probability that we started from I at time 0 and at Tn, for any value of n, Tn, what is the probability that the process will be at state j? So this is graphically, this means like this, that we started from state I at time t is equal to 0. What is the probability that at time n the process is in state j? So this is solved using this recursion based formula, where this is transition probability and this is the same R but for some different subscripts. Right, so when does Rij, the n-step probability, it converges if it is if the Markov chain contains a single aperiodic class, a recurrent class that is aperiodic. For periodic chains, it doesn't converge, it never converges. So it converges only for aperiodic class, and there may be recurrent states in the chain, and that is optional. So we have studied a number of examples in our previous lectures regarding convergence of Rij or Rij of n. Right, this means it becomes independent of initial state. For very large values of n, as n is very large, Rij of n is independent of n. So it is also written as Rij of n. Rij of n. So Rij of n not only becomes independent of n, but it also becomes independent of I if n is very large. So we can rewrite Rij of n by making it independent of I and n, and we replace this R with pi. So pi j can also be written as the transition probability of going from k to j, pi k. It's also a recursive formula. And we know that pi is the long-term probabilities for all states in the state space. Is of 1. And we call it normalization equation. Absorption probability, the next topic we studied was absorption probability. Absorption probability means that we start from a recurrent state, for example, in state number 3. In this case, what is the probability that starting from 3 will eventually be absorbed in either RC2 or RC1? These two are recurrent classes. The probability that eventually the process is absorbed in a given recurrent class. So starting point is always a transient state. And we find the probability that finally we will either be in RC1 or RC2 or RC3 or any RC, any recurrent class. Right. So for the class that we want to be in, we set AS is equal to 1, the probability of that equal to 1. And AI, we put AI is equal to 0 for all other absorbing states. We should write it all other here. So this AS is also for an absorbing state, but this is the absorbing state for which we are going to compute the probability of the process being absorbed finally in. So AS is equal to 1 for the targeted absorbing state, and this AI is equal to 1 for all other absorbing states. And this is the formula, the recursion based formula is computed for all other states, but they have to be transient states. For all transient states, we use this recursion based formula, and we compute, then we have to solve a set of linear equations, that are independent, and we make use of, and that are independent, and then we can calculate A's for all transient state. Starting from any transient state, what is the probability of being absorbed in a given absorbing state for which we have set A is equal to our 1. Right. So the last two items that we studied is time to absorption and some time, in fact, time related quantities. The time to absorption, given a state, for all recurrent states, we set mu I is equal to 0. Time to absorption means that how much time will it take to be finally absorbed in either here or here. Given many recurrent classes and many given transient states, starting from a given transient state, what is the probability that it will finally be absorbed either here or in any RCI? Can be anywhere. It can be any recurrent class, but the thing that is given is the starting transient state. So given transient state, so we'll compute mu I for all transient states, and we can test that starting from this transient state, what is the probability of finally being absorbed in a given in any of the absorbing states. So we'll put mu I is equal to 0 for all recurrent states. For all absorbing states, we'll put mu equal to 0, and mu of all transient states we will calculate using this recursion based formula. So and one of the two last things that we studied is the mean first passage time. This is defined for an RCI of a state. This is defined for a state that is a part of an RC, a recurrent chain. For example, this, maybe we have this 1 and 2, and maybe starting from 2, what is the probability of first passing through? Let's draw the full chain. So the question is that starting from 2, what is the probability of visiting 1 for the very first time? So we'll S is the targeted state. In this case, if you want to find out the probability of visiting state number 1 for the very first time, we'll put S is equal to 1. And then for all other states in this recurrent class, we'll use this recursion based formula to compute their TIs. Right. So if the question is that starting from 1, what is the probability of first visiting state 2, then we'll put T2 is equal to 0 instead of T1. We'll put T2 is equal to 0. Right. We already have solved a number of problems related to mean first passage time. And the last thing we studied under Markov processes is the recurrence time. Recurrence time means that given an RC, a recurrent class, for example, this, if I have visited state number 1 for the very first time, what is the mean time after which I'll visit state number 1 again? Or if I have visited state number 2, the process has visited state number 2, what is the average time after which state number 2 will be visited again? Right. So recurrence means visiting a state again. So visiting state S again. So we'll use this formula, and the Tj is the first visit time will be taken from this mean first passage time. So we have already solved an example related to recurrence time in our previous lecture. That's all for this lecture. I hope we will finish our mark our stochastic processes course with this lecture. Thank you.